double integral using polar form. So we have one integral problem, goes from -4 to +4, and then 0 to square root of 16 minus x squared e to the x squared plus y squared dy dx. So we want to complete this integral, but with algebraic process it is complicated because we are not able to integrate e to the x squared or e to the y squared. So we try to transfer this Cartesian form to the polar form, that when I have a small block, the length is dx and how wide it is called dy. So then area will be a equals dx dy. Now if you consider this one as a polar form, as you know, this line has angle theta, then it has another small angle d theta, and then we consider this small block here. That one you can see ds is the arc length from there, and dr is the small from the line. So in this case, we can say if I multiply dr with ds, that's the approximation of the area. Now from the pre-calculus, we have learned that the arc length here, ds, based on the angle they have here, and the radius will be ds equals r d theta. So then we can plug this one back here, we get dr times r d theta. So that is the block now, we can say approximation of dx dy in polar coordinate. So we will replace dy dx by r dr d theta. Now let us look at what is going on the limits. So x limit clearly we see is between -4 to +4, and y limit is between 0 to square root of 16 minus x squared. Now we understand that y equals square root of 16 minus x squared is a semicircle upward direction, this one. Because it's very easy to verify. If you square both sides, you get y squared equals 16 minus x squared. So that means x squared plus y squared equals 16. So that is the complete circle, but we are taking positive portion, so above x-axis. And if you carefully check, you will see the intercept here will be -4 to +4. And we are taking y from 0 to the curve. So this is basically the domain of integration. So in this domain, now let us determine what is r and what is theta. It's very clear that r is going from 0 to 4, as you see here. This is r. So you can have one circle here. This is your r. Then again it goes here. So this r goes from 0 to 4. That's your r limit. Now theta is starting from 0 and goes all the way, and the second part here, the second quadrant, then you can see it is between 0 to pi. So then my integral is ready now for the polar form. You can write first theta 0 to pi, then you have r is 0 to 4, and then e x squared plus y squared, as you know from polar coordinate, that x squared plus y squared is actually r squared, is that right? R squared. So we are saying e to the r squared, and dy dx will be replaced by r dr d theta. Now this integral is separable. I can write 0 to pi, that goes with theta, and then I have 0 to 4 r e to the r squared dr. So the first part, as you see, goes from 0 to pi for theta, and then this one r e to the r squared dr, you can go with u substitution. You say u equals r squared, and du will be 2r dr. So then r dr you can replace by 1/2 du. So that will bring here 1/2 du. So the integral basically now e to the u, which is e to the u, and u is r, e to the r squared, and the limit is 0 to 4. Now we got 1/2 pi, and then here e to the 16 minus e to the 0 is 1. And that's our integral. We complete this one. using polar form. Thank you.